Good morning, learners. My name is Mr. Pochilola. Once again, I represent Black Slides Online Education Masters. Welcome to topic number 13 of our Form 3 Physics. This is a topic which is called Electric Circuits, Energy and Power. Electric circuits, energy, and power. It's what we are going to discuss in this topic in today's lesson. Okay, so this is a topic which is going to run for 3 times, maybe 3 lessons, so to speak. Also, let me urge you to stay on. Watch the video up to the end and follow on the explanations, all the explanations. Every explanation is worth listening to. It's very, very important, right? Because if you don't, you are going to miss on the very pertinent points about the lesson. All right, so we are going to look at arrangement of resistors in a circuit. Remember that a circuit is a path. It's a path through which electric current flows, all right? And you also saw that resistors are simply electrical components which resist the flow of current, all right, resistors. So how do we arrange resistors in a circuit? There are 2 ways. You can arrange resistors in a series or along the same path, or you can arrange them in a parallel arrangement. So there are 2 ways to arrange resistors. You can arrange them in the same path. Remember that a series circuit consists of components that are arranged along the same path, or one after another, end-to-end manner, right? While a parallel circuit consists of components that are arranged in different paths or branches, all right? So please remember that, what series circuits are and parallel circuits are. So we can arrange resistors either in parallel or in series or in parallel. So we are also going to look at the what we call equivalent resistance, which is also called effective resistance. All right. Suppose you are given a network of resistors in a circuit, and you are asked to calculate the equivalent resistance or the effective resistance. What are they talking about? What it means is you should simply find the sum of the resistors that are being represented in the circuit. In other words, you are to calculate the total resistance. So in some cases, you'll be told to calculate total resistance. In other cases, you'll be asked to calculate equivalent resistance or effective resistance. It's the same thing. It's the same. All right? It's the same. All right? So master these terms, please, because you are likely to meet them in different past exam papers or in your Msce exams. They ask you calculate effective resistance or equivalent resistance, which is the same as simply finding the sum. So in this lesson, we are going to look at how do you find the sum of resistors when they are in series and also when they are in a parallel arrangement. All right, so let's look at the resistors in series. Resistors in series are said to be in series if and only if they are connected end to end, as shown here. You see, this is resistor 1, 2, 3, so they are connected in the same path. We say that they are connected end to end. In other words, they are in a series arrangement, all right? So we are saying resistors in series are said to be in series if they are in the same line, like they are here now. They are in the same line. So the same current passes through each resistor. Suppose that a current 2 ampere of current passes through R1 and through R2 as well as through R3. So we are saying if the current reading on the ammeter here is 2 ampere, all right? So that same 2 ampere flows through R1, R2, and R3s because this is a series circuit. Current through a series circuit is the same. So all these resistors are receiving the same amount of current. That is very important to note. It's very, very important to note. So the current anywhere in the circuit is common to all components connected to it. So in this case, the ammeter reading here, the current which the ammeter is reading there is equal to the current passing through each single resistor. All right. So let's look at the determination, how you can determine the effective resistance in a series circuit. Remember, effective resistance means total resistance, the amount of current, resistance in the whole circuit. Effective resistance. When you add the resistance of the different resistors, put them together, the value that you get, the magnitude of it, is effective resistance. So how can you determine? This is supposed to be determination, not determination, all right? So I beg your pardon there. So this is supposed to be an I, all right? So how do you carry out this experiment to find or to determine the total resistance in a series circuit? Great. So you shall need the following items. You'll need 2 resistors, 1 dry cell, a switch. You will need 3 voltmeters, connecting wires, as well as an ammeter. So please take note of the materials that you shall need in case in future I ask you to describe an experiment that could be done to determine the effective resistance in a series circuit. So these are the materials that you are going to require. So you connect the 2 resistors in series. Here we have R1 and R2. These 2 resistors are in series. So connect them in series as shown here. Then you close a switch. Close the switch there. Okay, and note the ammeter and voltmeter readings. So we have 2 ammeters. We have ammeter A1 and the ammeter A2. All right. Okay, and we have voltmeter V1 and the voltmeter V2, as well as this voltmeter here. So we have 3 voltmeters and the 2 ammeters. All right. So you look at, upon closing the switch there, look at the readings on the meters which we have. All right. Now, having done that, you are going to use the Ohm's law to find resistance R1 and R2. All right. So you use Ohm's law. Remember Ohm's law. Ohm's law says voltage is equal to current times resistance. So for V1 here, you simply take the current, which is the ammeter reading here, and this one is going to be given by the voltmeter there. So you make R1 the subject by simply dividing the voltage there by the current which is flowing through. So the current is the reading that you get from A1, all right, which is the same as that of A2. All right, so you do the same to find R2 here. You also use Ohm's law. Ohm's law is a very powerful relationship which helps you to carry out such calculations. So once you do that, it means you have values of R1 and R2. All right, so from the setup, we said that I1 is equal to A1 rather is equal to A2. The current that is read by ammeter A1 is the same as that of A2 because the circuit is series. The components are in a series setup. So current in a series circuit is uniform, is the same at all points. And also notice that the total voltage, okay, in a series circuit is just equal to the sum of the voltages dropped at each resistor. So the voltage dropped at R1 plus the voltage dropped at R2 gives us the total voltage. Please, you can rewind and have a look at the circuit again. So if we look at the current flowing through R1 and R2, we said these are in series as I, and we are saying that the total voltage V is equal to V1 plus V2 using Ohm's law again. Ohm's law, substituting V is equal to IR. Then what it means is that where there is V here, we can put IR. So here we put IRS. Remember that S is the total resistance. So IRS is equal to the current through resistor 1 times the resistance 1 plus current through resistor 2 times the resistance. All right. So if you look at the equation, you see I is common. You can cancel it safely, so that what you remains now as total resistance is this equation here. RS, which is the total resistance, is equal to R1 plus R2. All right, so if we continue adding more and more resistors in series, the result is that you are going to get higher resistance. The resistance is going to increase to be greater than any one of them. So in short, in a nutshell, the total resistance S in a series circuit is just the sum of the individual resistances. Right, so given a circuit in which resistors are in series, to find the total resistance, you simply add the resistances that are offered there. So the general equation for the sum of resistance in series is simply I1, R1 plus R2 plus and so on up to Rn, where n stands for the number of resistances. Please go through this a number of times until you are very, very sure that you are able to describe this experiment. Let's appreciate this in an example. Work out the combined resistance for the resistors shown here. So we have the first one here is 6 ohms plus 3 ohms. All right, since these two resistors are in series, it means the total resistance is simply the sum of the two. So in this case, it will be 6 plus 9, 6 plus 3 ohms, which is 9 ohms. You do the same here. You add 2 ohms plus 5 ohms plus 8 ohms. That should be capable of giving you 15 ohms. All right, as shown here. So the working out is simple. Just add R1. You can choose whichever is to be R1 and which one to be R2. So just add the two algebraically. You find the resultant resistance, the sum of the resistances. All right, so in this case, for the other part, you simply add the three resistors. In this case, you can again choose which one is R1, R2, R3. The order really is not quite important, but it is logical to label the first one from left to right as R1, R2, and R3. And then you find the total resistance. Just like that, no much mathematics going on there, just adding. All right. Let's also appreciate this other example. It's a good example. Sorry, it's presented in a different color, but as long as you are able to see, this is quite okay. All right, so here we are asked to find the value of x. So we have this x here. Okay, if the combined resistance of the resistors is 21. Since these resistors are in series, if you add all of them, 7 plus x plus 9, the result is 21. So all you have to do is to form an equation which links, you can call this R1, R2, and R3, so that R1 plus R2 plus R3 is equal to the total resistance, Rs. And then you substitute in the given values and the unknown. So in this case, you have 7 plus x plus 9, which is 21. Then you solve for x. So when you solve for x, it will give you 5 ohms. As simple as that. So resistors in series are so quite easily handled by simply adding the resistances. So here the unknown is x. The unknown could be any one of them. If x and another resistor were known, it means we could also solve for what we don't know using the same approach. Alright, so that is it about resistors in series. Let's appreciate how we handle resistors in a parallel circuit. Resistors in a parallel circuit. Alright, resistors in a parallel circuit. Resistors in a parallel circuit. Alright, how do we handle them? So, in parallel connections, resistors are connected side by side and their corresponding ends joined together. Alright, what we mean here is that we have these resistors connected side by side. You have this resistor R1 on top, followed by R2 in the middle, and R3 at the end. They are not in the same path. In other words, that's what we are saying. They are not in the same path. In other words, they are not in series, but they are in an arrangement which is called parallel arrangement or parallel connections. All right. So this one is a typical example of resistors in a parallel. So we have R1, R1, R2, R3, and each resistor is supplied with a different current. Okay, unless they are equal, all right, they can receive equal current. But what it means here is that the current read by the ammeter here, when it reaches this junction, it splits up, it is divided, it is shared to the resistors. All right, so if the three resistors have equal magnitude of resistance, then it means each one will receive the same amount of current. But it's not practical all the time to receive equal currents. Okay, it depends on the resistance of the resistors. Alright, so let's appreciate an example again, rather another experiment in which you are asked to determine the equivalent resistance given that the resistors are connected in a parallel arrangement. Alright, so here you are asked to describe an experiment that could be done to determine the equivalent resistance when resistors are connected in a parallel setup. Alright, so we have a parallel arrangement of resistors or network. Alright, so again here you will need the following items to complete the task. Alright, you shall need 3 resistors as before. You shall need 4 voltmeters. This time we have 4 voltmeters. Okay, and only one dry cell is going to do. Okay, you shall also need an ammeter, a switch, as well as connecting wires. Alright, so the setup is going to look like this. It appears to be a complicated setup, but if you follow on, you see that these 3 resistors are arranged side by side or in a parallel network. Alright, so you arrange the 3 resistors in parallel as shown. So we have resistor 1, resistor 2, and resistor 3 like that. Alright, and then you close the switch and note the ammeter and voltmeter readings. Remember that current cannot pass through a gap, so you close this switch here so that you bring about current. So when the current reaches a junction like here, it is going to split. It will be split so that all the resistors are supplied with current. So for each resistor, you apply Ohm's law again to determine the individual resistors. Remember, Ohm's law relates voltage to current and resistance. So very important. So you apply Ohm's law in each of the resistors to find the magnitude of the resistances. In other words, you are simply calculating the values of the resistors or resistances. All right. Now, having done that, you realize that the voltage supplied by the cell is equal to the voltage everywhere in the parallel circuit. All right. And also on calculation, you find that the total current, the circuit current that is equal to the sum of the individual currents supplied to each resistor. All right, so the voltage across R1, R2, and R3 is the same. Voltage in a parallel circuit is the same, all right, everywhere, okay? But current is divided up. So in this case, the total current I is equal to I1 plus I2 plus I3. So that when you apply Ohm's law, you find that the total voltage divided by the resistance in the whole parallel circuit will be given by the equal voltages divided by each of the resistances, like this, shown in the equation here. So if you play around with this equation, dividing everywhere by V, you end up having a neat equation which is given by 1 over total resistance equals to 1 over R1, or resistance supplied by resistance 1 and resistor 1, plus 1 over R2 plus 1 over R3, and so on. Don't forget to put a plus sign here. Plus a sign is very important to show that we are adding these things up. All right. So we are saying the total resistance is obtained by this relationship. It's a very powerful relationship in this topic. Okay, you cannot find total resistance unless you make use of this equation. It's a very powerful equation. Okay, so if two or more resistors are connected in a parallel arrangement, they give a lower resistance than any one of the resistors by itself. In other words, the total resistance in a parallel circuit is usually less, far less than any one of the resistors that are contributing to the sum. Alright, so if two or more resistors are in parallel, their combined resistance is given by this formula, like I told you. So it will be 1 over R1 plus 1 over R2 plus 1 over R3. And this will continue until you get the maximum number of resistors. Here, n stands for number of resistors, and the value of n is always an integer or whole number because we're just counting this. Okay, so we are saying this is the equation. In case you are given two resistors in parallel, you may not have to use this equation. There is a shortcut. There's a shortcut. It's simply R total is equal to the product over sum. So in this case, it will be R1 multiplied by R2 divided by the sum of these resistors. Okay, so we are saying in an exam, if there are only two resistors in parallel, just use this, we call it product over sum. So you have R1 multiplied by R2 divided by R1 plus R2. Then you make substitution of the values given, and then you find the magnitude of the resistance. That's not a big issue. Okay, so take note of this one in case there are only two resistors in a parallel setup. All right, let's appreciate 3 more examples here. We are told that, let's look at what we are given. we are told, or we are asked to calculate the combined resistance. Remember, combined resistance means sum. You just have to add the resistors up, okay? It will give you combined resistance. In some cases, instead of saying combined resistance, they will tell you to find or calculate the total resistance. Another term is effective resistance, or what we call equivalent resistance. All right, so equivalent, combined, effective, total, all those are referring to the sum of the resistors in a circuit. So do not be surprised when you see any one of those terms being used in a question. All right, so let's look at case A, in the first case. So here we are given the voltage 6 volts. The voltage supplied is 6 volts. And as far as parallel circuits are concerned, it means each of the resistors is receiving 6 volts. That, don't forget, is a fact which many students forget. As a result, they mess up in an exam. So we are saying voltage in a parallel circuit is the same. It's like in a house. All the lamps in your house are supplied by the same voltage because they are in a parallel setup. All right, so can you work out this one? Okay, here we have two resistors that are in parallel, 3 ohms and 6 ohms. Only these two are in parallel, but these ones are in a series arrangement. Okay, here only 6 ohms and 3 ohms are in parallel arrangement. Only this one is separate. Okay, so when you are handling situations like that, where you have some resistors in parallel circuit, others in series, all right, you start by dealing with the resistors that are in parallel, add them up, all right, treat them using the formula, the product over sum formula, because there are just 2 of them, all right. What you get there, you simply add algebraically to the resistors that are in a series. Okay, so you treat this as a parallel setup, and then the value you obtain, you add, literally add or algebraically add to 6 ohms and 4 ohms, just like that, you know. So, okay, similarly here, you treat this 6 ohms resistor and 3 ohms resistor in an algebraic manner, or rather using the formula for parallel setup, all right, product over sum, okay. What you get, add to 3 ohms. So that's the gist. It's not difficult to do that. You can do that, yeah. All right. So we are saying in the first case, since we have 3 resistors in parallel, all right, so you use the formula R over 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and then you substitute. You make substitution, whatever you get shall give you the total resistance. Okay, this is supposed to be an equal sign, not a plus sign again. All right, so that's what we have there. So you simplify this fraction, it will give you 6 over 12. But this is 1 over R. So this is 1 over R, but you are not looking for just an R. What is an R? What is R here? So you shall have to invert the fraction. So this bottom part goes up so that you have this 1 over 1 is the same. An operation done to one side of the equation should be done to the other side as well. So what you do to the left hand side, do the same, apply the same to the other side. All right, so when you invert both sides, then you're going to have 12 will go up and 6 shall come down here. So you simplify, it will give you 2 ohms as the sum. In case B, starting with either the series or parallel arrangement, remember, in series we have these 2 resistors, 6 plus 4, which is 10. And in parallel we have these 6 and 3, so you treat these as if they're in parallel circuit. Simplify. What you get, don't forget to invert. Get the denominator up and the numerator down. So you have 2 here. All right, this 2 is obtained by adding the resistors that are in parallel. Then at the very end, you add the 2. the one for series and that of parallel you add, it will give you the total resistance. Similarly, in the last bit here, starting with the parallel circuit, we get these two resistors, you add them up, but don't forget, whatever you get there, invert the fraction. The numerator goes down, the denominator goes up. And then the total resistance is found by adding the two, that of series plus that of parallel. All right, I'm sure you are okay with this, but if not, please don't hesitate to call or simply send me a voice note explaining your problem there. All right, having come this far, I would like to leave you now. But before I do, please have a look at these questions, which I want you to do, and send to me so that I can mark and give you feedback on the same. So take your time today and work on these questions. Please write neatly, because when you get back to school, I shall call for the books, and so that I can mark them through. But for the time being, just write and take a picture and then send to me on WhatsApp so that I can mark for now. All right? Okay. Please, if you're struggling, don't worry, don't hesitate to let me know, to ask me for help. All right, so far so good. This is only lesson number 1 of topic number 13. Remember, the teaching and learning stops next week on Friday. And if you're a Marymount student, it means that is the end of the holiday lessons. All right, so that you can prepare in week 7 for you are going back to school. But if you are not a Marymount student and you still want to continue learning, that is, if you're not going to any other school, we have another forum, separate paid app forum, where you can resubscribe or renew your subscription, and then you pay and continue learning if you are a home scholar. Okay, because these lessons are also suitable for you home scholars. So come next week on Friday, the forum will be deactivated because it was meant for the Marymount students, but you took advantage of that and you joined. That's fine. So if you wanted to extend your learning and you are not a Marymount student, let me know. Just send me a message that you want to continue learning even beyond Friday next week. We are going to make an arrangement for that. All right, so I look forward to the completed work, which you have to submit today. Make sure you practice all of them, and let me have a look at them. For now, it's a big bye-bye again.